All right, the first thing we need to do is star align all your files that you sent me. So I'm going to go ahead and do an image container. I'm going to open all the files you sent me. And then for star alignment, I'm going to select the luminance file you sent. And I don't need drizzle data. And I'm just going to go ahead and drop it on the image container, and it's going to star align them all. All right, now that they're all star aligned, I'm going to go ahead and rename them all. I do have some just little icons here to help the renaming process go a lot faster. So that's S2, that's red. I don't have one for open, so I'm just going to have to call that open. O3, luminance. I don't have one for H beta, H alpha, green, blue. Okay, and then you gotta do the cropping. So we need to crop them all exactly the same so we get rid of this artifact. So what I'm gonna do, and you may find this really useful, is open Pixel Math, go to Expression Editor, and we're gonna take the minimum of all the different files. So that's going to ensure that we can see the black border that's developed from every single one of these images. And we'll say create new. So this new file here has all the black border we got to crop out from all of them. So I'm going to go ahead and open our image container, get rid of all those files. We'll open our views that we have open. We don't need image 19. I'll make that our image container now. And now with image 19, we can go ahead and open dynamic crop and just crop our image here. That ensures we're going to get rid of all the border on all of them. And I'm going to just move that triangle over to our image container. It's going to go ahead and crop everything. And done. We can go ahead and close dynamic crop and close that image 19. Now they're all cropped exactly the same. I'm just going to go up to a window and cascade them all so they look easier to work with. Now at this point you're going to have to remove the gradients from each one. So I'm just going to use ADBE. You could use other ones. So I'm going to go script, SETI Astro, automatic DBE. Define an exclusion area. Now I'm going to define that exclusion area kind of around the Orion Nebula. We don't want any sample points getting stuck in the dark regions in there. And then just execute it. I'm going to execute it on all of them. I'll do them one at a time, and we'll be back when I finish all of it. Okay, I have gradient removal done on all of them. We're still all in the linear state. And the next thing to do is continuum subtraction. So script, SETI Astro, continuum subtraction utility. These are starry images, and we're just going to load them up. H alpha, oxygen, S2. S2 is going to fail, but just because I've done this a couple times. But you can see what's going on. And because we're going to want to do additional science with like dividing and stuff, we're going to just output the linear image only and not allow it to do auto stretching, since we want to control the stretch later. We could also say apply noise reduction within the process and use noise exterminator. If you don't have a noise exterminator, you could use Expert Denoise as well. I'm going to click execute. And we'll come back when that's finished. It's done. We'll have our 3 images here. And here's the hydrogen alpha narrowband continuum subtract data. Here's the oxygen continuum subtracted data. And then for sulfur, you're going to see that it overcorrected in the middle. And you're going to have to manually do sulfur. I've tried this a couple different ways. I've used the script by Night Photons, photometric continuum subtraction. I've also done my continuum subtraction utility with the starless method, both of which overcorrect sulfur. So let's go ahead and do this, the manual method for sulfur. We'll close that window. We'll do channel combination. We want S2 and red channels. All right, now that we have this image here, we want to use my script find background. Script SETI Astro find background. Again, I'm going to do an exclusion area because I don't want any background point getting found like in the nebulosity itself. And then just click search. All right, when it's done finding the background, we can go ahead and open up background neutralization. We can go ahead and drop the background in there. And then we'll open color calibration. We'll keep structure detection on. We'll do the background. And we also want a region of interest for the white point. So we're going to go ahead and do a preview area around Orion, because that's going to have a nice central continuum in the middle. And we're going to put that for the region of interest for the white point. And we'll leave all this checked and apply the apply the color calibration. And now we could run a linked STF, and there's our sulfur red image. Now we could do the continuum subtraction. It's very similar to the equation you had, but we know it's going to overcorrect, and that has to do with how the red filter and the S2 filter really don't line up very well. So the red filter is a poor example for the continuum for the S2 region, but it's the only thing we have, right? So let's try a 0.8 and see if that's enough to bring down the overcorrection. Still overcorrecting, so let's go with a 0.6. 0.6 is really close. I'm not sure how much more we're going to get. I mean, we can go down to only a 0.5. The problem is we're going to start getting continuum in the continuum subtracted image if we go much lower than this. So this is probably all the more we really want to go. It's just, like I said, it has to do with the S2 filter and the red filter really not being that great for matching up for this process. But this is S2 narrowband. And then for your H beta narrowband, we're going to have to go ahead and script SETI Astro continuum subtraction utility. Starry for oxygen, we're going to go ahead and put in our H beta, and then we'll put in the green. We want the linear image only, and we'll apply the noise reduction. These are all starry still, and then we'll hit execute. We're just going to have to rename it because it thinks it's oxygen, right? But it's actually your H beta filter. And then when we're done, here's your H beta narrowband. I mean, at this point now, it's a matter of however you want to try combining all this stuff together, right? I would recommend probably running star X and getting rid of all these continuum subtraction star artifacts. So let me do that quick. And you can see you definitely had some bloating in your optical train around the bluer images. So like the H beta, your blue and green channels all have bloated stars. So you know, we also have that to contend with here a little bit in these images. And there we go. Now you have your H alpha continuum subtracted, your H beta continuum subtracted, your S2 continuum subtracted, and your O3 continuum subtracted. Again, depending on how you're going to do your dividing and all that, you could just try right away just H alpha narrowband divided by H beta narrowband, and then we're going to divide the whole thing by like 100. Since we can't have any values over 1, it'll get clipped. Let's just go ahead and give that a go and see what that looks like. And there we go. There's your Balmer decrement. Looks very similar to the one you had with the lower brightness area in the signal here in the middle, as that's, you know, the hotter region, and then kind of the outer bits here are actually cooler in H alpha. And then also, since these are brighter over here in like the Running Man and this nebulosity over here, that's also because it's much cooler over there, right? There's almost no H beta off in this direction, so it is much, much, much cooler. And if you invert this whole thing, this really shows you quite a cool little heat map now, where the brighter areas here are going to be the hotter, and the darker areas are going to be cooler regions, right? And that only really makes sense on area with signal. Like this out over here is just noise, so that's not really a good representation of the temperature. But in the area where there's actually signal, this is your heat map down in here. I think it's really cool. Some real science.